Hello guys, welcome to another video from Theory channel. In this video, we're gonna solve the seventh question from Sipser textbook, and actually this is the first question that we will see NFAs, or better I say non-deterministic finite automata, and yes, this is a new issue in computational theory, so let's solve it together. Okay guys, as you can see here, this is the seventh question from book, and it says that give a state diagram of NFAs with the specific number of states recognizing each of the following languages. In all parts, the alphabet is 0 and 1. So, okay, actually I write all of the question here, and I will construct the NFA for all of them actually in my notebook. So let's solve it. The first part is that the language that W ends with 20 with true states. First of all, let me show you the actually definition of NFAs. The definition of NFAs is that a non-deterministic finite automata is a 5-tuple like this actually here, as you can see, where Q is finite set of states, sigma is finite set of actually alphabet or finite alphabet, and actually this is the most important part in NFA, the third part. Our transition function here is actually like this, and if you notice here, actually, or better I say pay attention here, we have epsilon as one of our transition in NFAs. In last sessions that we construct DFAs, in DFAs we don't have any transition for epsilon, but in NFAs we have a transition for epsilon, and actually we have the power set of our states here, and this is the most important part in definition of NFAs. The fourth part is like DFA, Q0 is the start state, and the final part is that our active state must be a subset of our state, and yes, that's it. And actually we know that our active states group is finite because our state is finite too. So yes, that's it. Here let's construct the DFA for this part actually. Actually in NFAs, let me tell you something. We know that in DFAs we have the transition for every part. We have a transition. Actually, if our alphabet, for example, is 1 and 0, we have a transition for 1 and 0 in every state. If we have these two states, we must have a transition for 0 here, or I don't know, like this, and a transition for 1, and in this state we must have a transition for 0 and 1, like this, or you can write it like this. I don't know, it based on your language, but in NFA there's a difference. We don't have this condition that we must have the transition for every alphabet. Actually in here we can have a transition for 1, but or better I say like this, we have a transition for 1, but we don't have any transition for 0, and this is okay. There's no problem in NFAs. And another part is that we have an epsilon transition actually like this. It means that actually better I'll show you this in examples that you will see later. Actually, so first let's construct the NFA for this part. The language that W ends with 20 with true states. So we know that if we want to actually recognize this string, or better say language with DFAs, it will become like this. Actually, we must check that our language is end or better say finish with 20, and it will become like this. So first of all, with DFAs, we know that here we have a transition for 1 here, and if we see just 1 0, we will reach this part, and if we see 1, we will back to this part here, and after that if we see another 0, we will reach our active state actually, And after that, if we see another 0, we will stay here. But if we see another 1, we will back to our first state. And actually, this can be your final answer, because we know that every NFA has an equivalence DFA, or better I say, NFAs are equal to DFA, and any DFA is kind of NFA, a specific NFA. So this can be your answer. But if I want to solve it with NFA, it will become like this actually. We have a transition for 0 and 1 here, and after that a transition for 0 and another transition for 0, and yes, this is our answer. And as you can see here, for recognizing some languages, we can use from NFA, and our answer will become so much easier, because if you take a notice, in NFAs we can have a 2 transition for one alphabet, like here and here we have 2 transition for 0 in this state. And we know that an NFA is not deterministic, so it will see every trees that made from your decisions, and if just one of them is your accept, it will accept your language. And yes, that's it. That was the first NFA for part A. Let's get to part B. Part B says that the language of exercise 1.c with 5 states. 1.c is that W contains the substring 0101, and we know that W is equal to x 0101 y for some x and y. Actually, x can be equal to anything, and also y can be equal to anything. I don't know, 0111 0110, anything. It does not matter for us. So let's construct the NFA. Actually, with NFA, it will become so simpler. You just have to write it like this. First of all, we actually define a transition for 0 and 1 in our first state. And after that, all we have to do is that define the transition for our pattern. And it will become like this. 0 for here, and after that 1 for here, and 0 for here, and after that another 1. And yes, that's it. And this is our active state actually. And if we see 0 or 1, after that we will stay here. And yes, that's it. Actually, the 0 and 1 here somehow show the x part, and 0 and 1 here actually somehow show the y part. And this is our pattern. You can see here. Yes, that's it. Let's go to next part. The next part, part C, the language of exercise 1.6, part L with 6 states. Actually, this question is that W contains an even number of zeros or contain exactly 2 ones. Actually, first of all, let me show you something about regular languages. So actually, yes, here, as you can see here, this is a proof from Sipser textbook. The class of regular languages is closed under the union operation. And the proof idea is that we have regular languages A1 and A2, and want to prove that the union of A1 and A2 is regular. So we want to prove this part actually. So the idea is to take 2 NFAs. We use from NFAs to prove these parts, N1 and N2 for A1 and A2, and combine them into one new NFA. So we construct a new NFA from N1 and N2. Machine N must accept its input if either N1 or N2 accept this input. The new machine has a new start state that branches to the start state of old machines with actually epsilon arrows. So we have epsilon arrows. In this way, the new machine deterministically guesses which of the 2 machines accept the input. If one of them accept the input, N will accept it too. So if one of them accept the input, n will accept it too. We represent this construction in the following figure. On the left, we indicate the start and accept states of machines n1 and n2 with large circle and some additional state with a small circle. On the right, we show how to combine n1 and n2 into n by adding additional transition arrow. So as we can see here, this is the n1 and this is n2. So all we have to do is that actually define a new state that is here and use from epsilon arrows to actually enter n1 and n2 here. And yes, that's it. This is the union of two regular languages, and with this method we can construct an NFA for our languages. So yes, let's back to our question. So first, let's break our question into actually two parts. The first part is that W contains an even number of zeros, and the second part is that W contains exactly two ones. So first, actually we can use from DFAs for, actually we know L1 is that W contains an even number of zeros, and yes, this is for L1. And for L2, we know that W must have exactly actually two ones. So first, let's construct the DFA for L1 and then construct the DFA for L2. And after that, we use from the method that I show you for the union of two languages and construct a final NFA for both of them. So first for L1. For L1, our language is like this actually. We must contain an even number of zeros. So we know that 0 is an even number, so this is our accept state, and after that, if we see another 0, we will reach this state, and if we see another 0 after that, we will back to our accept state. And we know that number of 1 is not important, so if we see any 1, we will stay in our state. So this is for L1. For L2, we know that W must contain exactly two ones. So let's construct the DFA. It is so simple later. The number of 0 here it's not important for us. So if we see any 0, we will stay in our state. And if we see a 1, we will reach this state. And again, the number of 0 it's not important. And if we see another 1, we reach this state that is our accept state, because here we have actually 2, 1, and after that the number of 0 it's not important. But actually pay attention to this part. If I want to construct a full DFA for this part, I must add another state for here. If we go over 2 1s, and it will become like this actually. But I can use from the property of NFAs and construct the NFA like this. We know that if I want to construct a DFA, I must define a transition for 1 here. But in NFA, there is no condition that I have to define here. So yes, this is the NFA for L1, and actually for L1 and L2. So now let's construct the final NFA for union of L1 and L2. Based on our method, we will actually define a new state, a starter state actually like this, and define these actually epsilon arrows here and here, and after that we will actually draw our normal NFAs. So it will become like this for here. Yes, this is our accept state, and for L1 it will become like this. Actually, you know that number of 1 does not matter for us, so it will become like this here. And yes, this is the final NFA for union of L1 and L2, or better I say for L language. So let's go to next part. The next part is that the language actually zero. We must recognize the input 0 with to state, only to state. We know that 0 is not epsilon, so I can't assume our start state as my accept state. So it will become actually like this. If I see just 1 0, I will reach my accept state. And yes, that's it. This is all matter. So let's go to next part. The next part actually is that the language 0 star, 1 star, and 0 plus actually with 3 states. So first of all, let me show you something from the actually first from a star operation. Based on a Sipser textbook, the class of regular languages is closed under the star operation. Proof idea is that we have a regular language. We have a regular language A1 and want to prove that A1 star also is regular. We take an NFA N1 for A1 and modify it to recognize A1 star. So we take an NFA N1 for A1 and modify it to recognize A1 star. As shown in the following figure, the resulting NFA N will accept its input whenever it can be broken into several pieces, and N1 accept each piece. So it will become actually like this here. And after that, we can construct N like N1 with additional epsilon arrows returning to the start state from accept state. This way, when processing gets to the end of the piece that N1 accepts, the machine N has the option of jumping back to the start state to try to read another piece that N1 accepts. In addition, we must modify N so that it accepts epsilon, which always is a member of A1 star. One slightly bad idea is is simply to add the starter state to the set of accept state. This approach certainly adds epsilon to the recognized language, but it may also add another undesired string, like exercise 1.50 asks for an example of the failure of this idea that we will solve it later. The way to fix it is to add a new start state, which also is an accept state, and which has an epsilon arrow to the old start state. This solution has the desired effect of adding epsilon to the language without adding anything else. So actually, if we assume this part as our NFA for A1, if I want to construct a final DFA for A1 star, it will become like this. We draw epsilon arrows from our accept states to the starter state of N1. Actually here, this is a start state of N1. And before that, we actually define a new start state that is our accept state 2, and define another epsilon arrow to the start state of N1. So actually this is the proof that the regular languages is closed under the star operation. And also I have to show that the regular languages are closed under concatenation. And if you pay attention to this part, The proof idea is that we have regular languages A1 and A2 want to prove that A1 concatenate with A2 is regular. The idea is to take two NFAs, N1 and N2 for A1 and A2, and combine them into a new NFA N as we did for the case of union, but this time in a different way as shown in figure 1.48. Assign n's starter state to be the starter state of n1. The accepted state of n1 have additional epsilon arrows that non-deterministically allow breaching to n2 whenever n1 is in an accepted state, signifying that it has found an initial piece of the input that constitutes a string in A1. The accepted state of n are the accepted state of n2 only. Therefore, it accepts when the input can be split into two parts. The first part accepted by n1 and the second by n2. We can think of n as non-deterministically guessing where to make the split. So this is the figure 1.48 actually here. As you can see, if we have n1 and n2 and we want to actually recognize the language that n1 concatenates with n2, we must add some epsilon arrows here from accepted state of n1 to a starter state of n2, and it will become actually like this here, and our accepted state will become the accepted state of n2. And yes, this is the way of recognizing the concatenation of two languages. So let's back to the question actually. In this part, we must recognizing the language 0 star, 1 star, 0 plus with 3 state actually. So first of all, let's construct the NFA for 0 star, and it will become like this actually. For 0 star, it is like this. Yes. Sorry. This is for 0 star. For 1 star, it will become like this. Yes. And for 0 plus, actually, it will become like this. We must have a 0, and after that, we are in our accepted state. So, yes, that's it. First, we draw the NFA for concatenation of 0 star and 1 star. So, for 0 star, 1 star, it will become actually like this based on our method. We have a state for 0 star here, and after that we have a epsilon arrows, and yes, it will become like this. So this is for 0 star, 1 star, and finally, if I want to construct the final NFA for our language, it will become like this. For 0 star, 1 star, and 0 plus, it will become actually like this. We have a transition for 0 here, and after that, and actually we have a epsilon arrow like this. And sorry, actually I make a mistake here. We know that after concatenation, our accepted state will become the accepted state of the second part. So our accepted state in this language is here actually. So for this part, 0 star, 1 star, and 0 plus. In this part, we have a transition for 1. And after that, we must draw a transition for 0 because we must recognize 0 plus, not 0 star. So we use 0 instead of epsilon arrows, actually. And it will become like this. Yes. This is the final NFA for 0 star, 1 star, and 0 plus. Yes, that's it. Let's go to next part. The next part is that the language 1 star and 0, 0, 1 plus, that came with a star. So if I want to construct the NFA for you, actually with three state, notice that here we must construct the NFA for with three state. It will become like this actually. Sorry, yes. We have a transition for one here because we must recognize this language contain a string one. So yes, actually it will contain epsilon. So our start state must be our accept state. So yes, this is our accept state here. And after that, if we see one, we will stay here because we have one star here. But after that, if we see 0, we must go to this state here. And after that, if we see another 0, we must go to this state here. And finally, if we see just 1 here, we will back to our accept state. And yes, that's it. This is the NFA for language in part F. Let's go to next part. Part G says that we must construct an NFA for the language that actually just accept epsilon with one state. We know that if we accept epsilon, our start state is our accept state actually. So it will become like this, and that's it. We don't have to add any extra transition to it. For example, if we add 0, in here, actually we can accept the language that accepts 0 star, and we don't want something like this. We only want to accept epsilon. So we will delete this, and this is the only answer here. This is the answer for part G. Okay, now let's go for part H and the final part. The part 8 says that you must construct NFA for the language that accepts 0 star with one state. So based on things that I show you for implementation, or better I say construction of NFA based on S star, our NFA will become something like this here. Because as you can see, if we actually assume our string is equal to 0, we accept it, or epsilon, actually we accept it again, and this NFA actually accept every string that we can construct with only alphabet 0. And yes, that's it. We solve every part in this question, and actually this question was so useful. You can learn a lot of things about NFAs in this question actually. And I hope you guys enjoyed this video. If you like it, actually like this video and subscribe to my channel. And if you have any comment, drop it for me. I will read all of them. And you know, this is a big motivation for me that I read your comments, see your like in my videos. And yes, that's it. I hope you guys actually enjoyed this video. Have a nice day, guys. Goodbye.